Once again for the opportunity to be here and talk with everyone about MR hardware. And in this case, I am bringing some examples from what we have done in our lab in building our own MR system. So going directly into the lecture, as we probably have known now, that MR involves generating and manipulating several magnetic fields. And sometimes the skill comes into manipulating those fields for you to be able to get what you need from the MR system. And those magnetic fields include the main magnetic field, which we will see, the shimming magnetic fields in case your main magnetic field is not very uniform, then the gradient magnetic fields, the radio frequency magnetic fields, and then the associated hardware for control systems that make the system complete. And that constitutes your MR hardware. And like we have said, it includes the main field, which is a large magnetic field, the radio frequency field, which varies at a certain frequency, the gradient magnetic field, which are linearly changing in space, which are used for encoding, and then the control systems, the computers, and all the programs and softwares that many people write to help control the systems. So if you put these into perspective, the main magnetic field is usually a cylindrical system. Some are open systems, but the cylindrical ones are pretty common. And the rest of the fields or the circuits that generate those fields are mostly inside or coaxial to the main magnetic field in order to leave a bore or a space where you can have your patient or whatever you want to image. For those who image animals, fruits, and the like, whatever you want to image has to have some space inside there for you to be able to have a good imaging. So the main magnetic field, as we now know, is a very strong, relatively strong magnetic field compared to the rest of the magnetic fields that are generated. And it is used for polarization of the spins. The main magnetic field should be stable over a period of time. That if you are generating 1.5 kilowatt, 1.5 Tesla, you should have 1.5 Tesla today, and 10 years later, you should still have 1.5 Tesla. It should be spatially uniform, that within the imaging volume, if it is 1.5 Tesla at x is equal to 3, it should be 1.5 Tesla at x equal to 0. So you should have a uniform magnetic field within the working volume. The other considerations of the main magnetic fields are, of course, the weight. The main magnetic field normally carries or brings with it the bulk of the weight of the MR system, which can go into thousands of kilograms. But the other consideration is, of course, the size of the bore. If you are making for patients, there is a minimum size of the bore below which you cannot go before you fail to image any patient. And also the operating costs of the system. The main magnetic field also comes with some operating costs depending on the material that you use for making that main magnetic field. The main magnetic field normally is made out of, can be classified into 3 categories. You can make it using permanent magnets. You can also use resistive magnets and superconducting magnets, okay, depending on your application and what you are able to achieve and the degree of complexity that you want to go into, the cost that we talked about earlier, the weight and all that. You can decide accordingly on what is feasible for you? Do you have permanent magnets? Do you have resistive magnets that you can drive at high currents without them melting? Or you have access to superconducting magnets or abilities? So the technologies generally vary between various specifications so that the optimum choice of the magnet will depend on the demands of the clinical applications or what you anticipate to do with the system. But if we look at the permanent magnets, traditionally we have had permanent magnets that look a little like this: open bore or a bit of cylindrical bore in a way to generate strong magnetic fields. So you have your patient or whatever you want to image within that volume that the magnets subtend between them. So they are composed of either one piece. You can have a big block piece of magnet, or you can have several pieces that are arranged in a certain way for you to achieve a certain magnetic field strength and volume. Okay, but the magnets might provide closed access or open access to the patient. So some of the permanent magnet systems, the old ones, open magnets, which are preferable for patients who fear closed environments of claustrophobia. This might be a better option for them, that you are able to see the outside world when you are being imaged. The magnetic materials that are normally used for these are neodymium iron boron magnets or aluminium nickel cobalt magnets. So these also provide varying magnetic field strength, and for you to achieve a certain field strength, you might need a certain amount or volume of those magnets, and that contributes to the weight of the magnet as well. It is relatively challenging to achieve a homogeneous magnetic field using permanent magnets. So the allowable limits might be difficult to achieve, especially if you are building yours locally, but still you can be able to achieve them. Most permanent magnets generate pretty much less than 0.5 Tesla for many of them. A number of them are 0.35, 0.2 Tesla magnetic fields, because if you are to generate higher magnetic fields, given a certain volume, then your weight grows exponentially and becomes difficult to probably achieve those high magnetic fields. They are generally heavier than electromagnets, given the magnetic field that you want to generate. But if you are in very low field magnetic fields, then you can also have systems that are pretty much portable in the context of MRI. The weight also depends on the choice of the magnetic material. Okay, for example, 0.2 Tesla whole body magnet constructed from iron might weigh up to 25 tons, and a comparable system made of neodymium magnets might be just about 5 tons. But you can see we are still talking about 5 tons. Whether it is 5 tons or 25 tons, it's relatively heavy. And if you are using machinery to carry, probably the difference between 5 and 25 is not so much. You still have to bring a crane anyway to carry any of them. So that might not be a very big problem. But the size, the physical size, the footprint of the system then also matters a lot. A 25-ton system might have a relatively bigger footprint than a 5-ton system. So that might also limit how far you want to go in terms of weight. So while the field strength of permanent magnets is limited and their weight is high, they consume relatively no electrical power, if I would say, and they dissipate no heat, and they are very stable in terms of temporal variation of magnetic field over time. So long as you maintain the temperatures, you relatively keep the same magnetic field over a long period of time. So you have advantage that you are able to generate a magnetic field without additional bills, if I would say, in terms of power consumption, maybe in terms of cryogens for cooling and things like that. So it might be heavy, but relatively cheap in terms of running costs. So once you have installed it, it is inexpensive to maintain. The challenge is manufacturing it and installing it. There has relatively been a new way of constructing permanent magnets called the Hallback array systems that you can arrange small magnets. In our lab, we use about 1-inch magnet, 2.54 centimeters cubed. And if you arrange them in a certain manner, you can increase the magnetic field on one side and reduce the magnetic field on the other. So if you are skillful enough and you arrange this in a circular cylindrical manner, you are able to generate a magnetic field inside the bore and a relatively very low magnetic field extending not more than 5 centimeters outside the bore. So the fringe magnets can be pretty much low. This is an example of a Hallback array system that we have in our lab with an imaging volume of about 32 centimeters and a length of about 55 centimeters, only generating just about 4850 millitesla in magnetic field strength. And one good thing with some of these systems is that you can build it within your lab and you can print some of the parts by yourself if you have the design, or if you can design it. You can also, you have a good 3D printer, you can print some of the rings within your lab or laser cut them from materials such as plexiglass or acrylic glass, which can be relatively cheap in a way. So this was my team trying to assemble our system in our lab to generate a magnetic field. At the time, we had wanted a 50 millitesla system, but you can see the bunch of magnets at the corner here that we use for putting into those rings to create a magnet. And when you arrange it in a way, you end up with a magnet that looks like that. And I suppose that many of you will be constructing this in the summer to see how easy or how difficult it is to assemble a system like that. But these are relatively portable systems that I said you can put at the side of the bed. You can image small samples, but even a head of a human being should be able to fit in. The only limitation is that it's a little bit difficult to increase the bore size to fit, for instance, a human torso without the system becoming pretty much not portable again, if I would say, because the weight grows up pretty quickly. So our system here is about 80 kilograms in weight. That constitutes the magnets and some of the supporting infrastructure to hoist the magnet up. That's about 50 kilograms, 80 kilograms in weight. And the rest of the magnet, like we are going to see, mostly electromagnets. So after you have made your permanent magnet using the main magnetic field using permanent magnets, then the rest of the systems are electromagnets. But also depending on your strength of magnetic field, if you are generating 50 millitesla, then the rest are also relatively very low magnetic fields. You are talking of things like maybe 0.5 Tesla or some millitesla or something like that. So you also have very little current driving the rest of the system. So our system operates on about 63 watts of power, which is battery power, if I would say. You could run it on a battery. But you need to specify the applications of the system that you are going to make as well, because like I said, you could probably not image a torso or do functional MRI with these systems. However, as technology improves, we think that things like neuroimaging will be possible with these systems in the coming years. So while it is possible to make them in magnetic fields using permanent magnet, the rest of the magnets need to have some sort of variability in their function. So it is difficult to make them using permanent magnets. Because if you need a magnet that varies over time, you need the magnetic strength that varies over space, you cannot at will control permanent magnets to vary their field according to what you wish. So it becomes difficult to make the rest of the magnetic fields as permanent magnets. So you then go to electromagnets, okay? And electromagnets, you can use resistive wires for making electromagnets. You can also use superconducting wire, which limits the ability of where you construct the system from. Because if you are using superconducting wire, then your manufacturing environment might not be, your lab might not be suitable for making such a system. But electromagnets can produce relatively very high magnetic fields or strong magnetic fields, so long as they can drive sufficient current through the wire without excessive heating or a lot of power being consumed within the systems. Many of the magnetic fields or coils that generate the magnetic fields are solenoid coils. And as you can imagine, that the magnetic field of a solenoid coil increases with the current that you drive into the coil, but also with the number of turns that you put into the coil. So as you increase the number of turns, you are increasing the magnetic field, but you are inadvertently also increasing resistance and increasing the weight of the magnet. So as you make many turns, you also make the system heavy, and you increase resistance, so you increase power consumption, heat dissipation, and things like that. And the solenoids normally generate fields that are not really very uniform. So you might, if you need a very uniform magnetic field, using solenoids, you might need to apply some correction mechanisms to make sure that the magnetic field is homogeneous. But they are very simple to construct and they are easy to learn with, as you can imagine. The requirements for heat generation and power consumption increases, of course, as the square of the current. So however little current you put in there, when you square it, becomes relatively big current, and that can generate a lot of heat or a lot of energy that is needed to drive the system. The field stability of electromagnets is also an aspect that sometimes disturbs or is a little bit difficult to conform to, because as the coils heat up, their resistance changes, the current that drives them then change, and that might cause variability or inhomogeneities in the magnetic fields. So the circuits that normally drive these fields are sort of specialized kind of circuits that can provide stable current over a variable resistive device, if I would say, or a variable resistive coil. So as the resistance changes, the current through should remain the same. So you might find some of the lab devices that you use for driving these are relatively very expensive compared to other normal laboratory power supplies. So the requirements are technically difficult to achieve and further restrict the performance of the resistive magnet systems. Okay. However, you can build resistive magnet system probably up to around 0.2 Tesla before the power consumption or the energy requirement overwhelms you. So they are generally lighter in weight than permanent magnets of comparable strength, although the power supply and cooling equipment required for their operations add weight and space onto what you need. So we have not only built permanent magnet systems, we have also tried to build resistive magnet coils, and you can see me there winding a solenoid coil to use in our pre-pulse system. And we have also tried to carry some imaging with that. You can see some of our images that we generated with a system like that. And again, this was less than 50 millitesla in magnetic field strength for the main magnetic field. However, it needed up to about 6 kilowatts of power. So compared to the permanent magnet system, which I said were operating on 63 watts, these we are already reaching 6 kilowatts of power, only to be able to generate about 50 millitesla. So you can see that if you want to increase that to maybe 0.1 Tesla, this power will grow exponentially. And the system would also hit if we run the system for about 45 minutes. The temperature inside the bore, in the coils, not inside the bore, the temperature inside the coils would reach about 90 degrees Celsius. So we are almost reaching boiling point of water. So you could probably not put anybody inside that thing. No patient willfully will accept to go inside the system like that, because the temperature inside the bore would also be in the 50s, even with free airflow. So you realize that this system already needed cooling. And when you include cooling into the mix, the system becomes a little bit complex. So that is when superconducting electromagnets become important, or they become a little bit appealing, because if you want to increase the magnetic field, you might need to cool the conductors down. And if you are able to do that, if you reach temperatures where the conductors are then superconducting, then you can pump as much current as possible. And with your magnetic field increasing as the current, then you can have a relatively strong magnetic field. However, superconducting magnets also have their own challenges. You need to cool the conductors to about 4 degrees K. And this is a hard task to achieve in a small lab, if I would say. But if you are able to achieve that, then the power consumption of that system also reduces, because then you need to energize the system once, and you don't need to provide continuous power, continuous energy into the system. So long as it is energized and there is zero resistance, you are sure that the system will continue in operation indefinitely, if I would say, without you injecting more energy into the system. But then you have to maintain the temperatures pretty low to be able to do that. So in environments where we have regular power outages, for instance, then maintaining such systems become a little bit difficult, because then now you have to run diesel generators that consume a lot of power and things like that. So it's a cumbersome system, especially for the low and middle income countries. So because of the need to maintain sufficient liquid helium, which you can use for cooling, you have to have some sort of insulation into the system as well, because the helium can evaporate. So sometimes you have to surround the helium itself with nitrogen to keep the cool temperatures in the system and things like that. However, if you have the means to do that, it's an excellent system that everybody would wish to have. Unfortunately, it has its own challenges that prevent many people from accessing such a system. And as you can see, such systems are normally huge in size and in weight to accommodate, provide the vacuum and space for also the cooling cryogens into the system. In summary, we have talked about the main magnet now, in which case we have talked about the permanent iron core magnets, which we say are low and open, the resistive electromagnets, which we say you can go up to a limit of about 0.2 Tesla, and the superconducting magnets, which can go at the moment up to about 35 Tesla. I think there are systems that might reach about 42 Tesla as research systems. So you can see that you can really generate very strong magnetic fields using superconducting magnets. Citing considerations, we are not going to talk about that much. We want to go to the rest of the magnets that we have. But as you can imagine that depending on the type of magnet that you have, where you locate it also matters quite a bit, okay? Because you might need to shield the room to prevent stray magnetic fields, to prevent people from walking into the system. You can't take it closer to the patients. It has to be fixed or something like that. So depending on the magnet that you have, the siting or locations then matter a lot. But the field stability. So when we talk about shimming, we talked about the other type of magnetic fields or the magnets that we need to generate, shimming magnets. So sometimes you can construct a magnet like this, and when you do the mapping of the magnetic field inside the working volume, you find that the magnetic field is not necessarily very uniform. So you have regions of high magnetic field and regions of relatively low magnetic field. This changes your alarm frequencies within the volume and becomes very difficult to image. So you have to have shimming magnets that you place at certain points, either to cancel the magnetic field or to add on to the magnetic field so that you have a relatively uniform magnetic field over a given volume. I had designs of our shim magnets here for our system, but I have forgotten to include them in the slide. I have them in another slide. I will probably share if anybody needs. Okay. So you can have a passive shimming system, which you can again use permanent magnets for shimming or iron poles that you insert at certain specific points, or you can have active shimming systems in which you have coils that generate magnetic fields depending on the need as and when you need the magnetic field to be uniform. So if you look at, for instance, in superconducting electromagnet, the superconducting shims are additional coils of superconducting wire that are wound coaxially with the main magnetic field. And you can see, for instance, an example here. You see that on one side you generate relatively high magnetic field. On the other side, you generate a very low magnetic field. So if you are to insert this into the bore of the system, regions that have low magnetic field, you can add on to them, and regions that have less magnetic field, you can subtract from them so that you have a relatively uniform magnetic field within your working volume. the hours are passive shims because we are using shim magnet or permanent magnets to insert in certain regions in certain ways to provide either an addition or a subtraction of the magnetic field. Most of this is the explanation of what I am talking about, and if anybody needs, they can. I will share the slides in case anyone needs to follow up with some of the explanations that I am talking about. But the other important hardware of the magnetic field within which it will be, without which it will be very difficult to perform imaging are the gradient magnetic fields. And these gradient magnetic fields provide a special invariant field within the X, Y, and Z direction of the magnet. And you have to wind them also inside and insert them inside the main magnet. So normally the Z direction is like the direction along the bore of the magnet, so you can use an anti-Helmholtz coils that provide the magnetic field along the Z direction. But XY gradient coils also have to provide magnetic fields in the X and Y direction, and therefore their configuration is relatively different from what you'd have as a Z magnet. So whether you are using permanent magnets, you might still need gradient coils that are made of electromagnets. Know that you might be able to provide a standing gradient using permanent magnets, but its application can be very limited. You might have very few applications for that kind of gradient coil. So if you are to see, for instance, here, we could say that the green ones are the Z gradient magnetic, Z gradient coils, and the red and yellow are X and Y gradient coils, depending on what you consider as X and what you consider as Y. So these are normally, you'd wish to run them at room temperature. So that means you have to be conscious about the currents that you pump in there and also the resistance of the systems. So a gradient along the Z, for instance, you can wind this easily. As you saw behind there, I was winding some electromagnets. Some of them were this kind of magnets. So if you have coils like these and you run current through them in opposite direction, you are going to have a magnetic field at the center of the coils, which is relatively zero, increasing from the center going towards the coil and then also on the other side. So you end up with a specially varying magnetic field, negative on one side, growing up to zero and growing up to positive on the other side of the magnetic field. If you are making the X and Y gradients, you need a pair of coils to be able to do that. And the most common ones are the Gole coils, most common and also relatively easy to make. As you can see down here in this photo, some of our gradient holders, gradient coil holders are here, and somewhere here you can see some black wires running around when we are making our gradient magnetic fields. And they're inserted inside here. If you see the magnet at the corner, lower corner here, you see, you can see where we have inserted our gradient magnetic fields or gradient coils. So that also starts to limit the space, the working volume within the magnet that you have constructed. So you could have aimed for 50 centimeters, but when you start putting these gradient coils in, your working volume starts to reduce, as you can imagine. Okay, so these gradient coils are used for encoding, like I said, special encoding and frequency encoding. And later on, when you go to talk about imaging, you will learn about how these gradient coils are used. For now, we are just talking about the types of magnetic fields that we need to generate in order to be able to carry out imaging. The last type of magnetic field that we need in an MR system is the radio frequency magnetic field. This is a field that induces energy into the patient or the system that you are imaging, and also receives energy that is emitted from the patient or from whatever you are imaging, and analyzes it and makes it into a useful signal that you can later generate an image from. Let me just check. I hope that I am not talking alone. I hope that people can hear me. Can I hear anybody respond if they can hear me?
Yes, yes.
Yes, doctor.
I think.
Oh, thank you. Thank you. Yeah, one time I was talking like this, I didn't know my power had already gone and my internet was off, and kept talking for like 5 minutes and there was nobody. So I'm happy that at least you can hear me. So in MR scanners, radio frequency magnetic fields are very necessary, okay? Because they are the ones that the main magnetic field sets for us the resonant frequency, and we use the RF magnetic fields to generate magnetic fields at that resonant frequency. So these are very important in trying to carry out imaging. So they are transmit coils, and they are used to transmit electromagnetic waves into the sample, creating an oscillating magnetic field, sometimes referred to as B1. If you compare it to B naught, they are orders of magnitude normally smaller than B naught, but the frequencies have to match the magnetic field set by the B naught magnet. So typical values of the magnetic field strength B naught encountered in MRI instruments, these signals lie in the radio frequency region of the electromagnetic spectrum, and we are able to run them at those frequencies. So the circuitry that you build for controlling this system, as we were talking about the hardware in the beginning, we talked about the magnets, and we talked about the associated hardware that control these magnetic fields. So building circuits that run at these types of frequencies can be relatively high, can be relatively difficult at 128 megahertz, 64 megahertz. In our case, about 2 megahertz that we run. So we have to have circuitry that do that. And many of these circuits are what we call the LRC circuits. You need an oscillator, and these are provided mostly by capacitors, okay, and inductors and resistors. So as you are building your coil, you inadvertently have resistance embedded in there, because the coil has resistance. As you make loops, you inadvertently are also creating an inductor. So in a way, if you take, for instance, a solenoid, by the time you finish winding it, you already have a resistance in there, you already have an inductor in there. So all you need to add is a capacitor. Sometimes you might need to add some resistance in to try and match certain resistances. But you realize then that if you are to reduce the resistance, for instance, you might need to cut the length of the coil. If you are to reduce the inductance, you might need to remove a certain loop and either cut it off or make it straight. So this becomes very difficult for you to vary. The thing that you can easily vary is the capacitor. So you can easily solder and desolder and put back capacitors into the system, or you can have variable capacitors that you can easily adjust within the system. So the capacitor then becomes a very good ally of us, and therefore the resonant frequency is set mostly by the capacitor, because as I said, your inductor is almost in there already when you do the winding of the coil. So the capacitor is what you have to play around with. So with your inductance and capacitance, you can set the resonant frequency at which your system should be able to oscillate. So as you build solenoid, as you build RF coils or radio frequency coils, again, the most common and easier to build is a solenoid coil, which you can put over your head. Unfortunately, it also might cover your face and you might not be able to see very far. So then you need to, again, start making some considerations on how you can make the coil more user-friendly, not just being easier to build. So there are different kinds of coils. You can have the solenoid coils, you have surface coils, you have bad cage coils, for instance, and I forgot to put a picture of some of our coils as well, but we have solenoid coils mostly into the system. We have tried to have some gole coils, some bad cage coils as well. But as you build a system, you realize that the solenoid coils are relatively more sensitive and can pick up more signal than some of these other coils, even though they would be more user-friendly than the solenoid coils. So RF coils create a B1 magnetic field, which rotates the net magnetization during imaging, and you can be able to transmit a magnetic field, but you can also use it as a receiver. So you can have two RF coils, one as a transmitter, one as a receiver, but you can also use one both as a transmitter and as a receiver. That means your control has to be well. You transmit, wait and receive, transmit, wait and receive. If you have a transmit and a receiver, you can pretty much transmit continuously, so you might be able to image faster than somebody who has one coil. Okay. So the RF solenoid coils, the configuration used for magnet and shim coils is also useful for RF antennas, for instance. When you are driving a solenoid coil with an alternating current, you generate a specially varying magnetic field, B1, which has the same frequency as the driving current. So if you need to generate a magnetic field at 128 megahertz, then you need a current source which will also run at 128 megahertz. So you start to realize that some of those current sources start to become a little bit pricey with time because of their special applications. Okay. Like we said, they're used to spin to turn to rotate the spins in a certain direction and allows the spins to come back as you record the energy that the spins are releasing as they try to realign themselves to the original position. So this works in conjunction with B naught as the main magnetic field. So generally, those are the different magnetic fields that we need to generate and constitute the bulk of the hardware of MR. The main magnetic field, the gradient magnetic fields, the shimming magnetic fields, the radio frequency magnetic fields. So if you are building an MR system for imaging, those are the major fields you need to generate. If your application is different, then depending on what you need to achieve, you might reduce some of these magnetic fields, but that is mostly the basic MR Hardware. And I'm trying to be conscious of time. I can see that I have a few minutes left, but I am also done. These are just now some of the photos and pictures of the different types of coils that are available. For instance, you have a surface coil somewhere here. You have a volume coil or the so-called bird cage coil somewhere there, and provides a variety of applications and some flexibility in what you need to image. If you see an array of coils here, you can have a head coil, you can have a neck coil, the shoulder coil, the knee coil, and these are all radio frequency coils. So depending on what you need to image and the orientation of your B-Note magnetic field, you can make an appropriate radio frequency coil, because normally we would wish to transmit the radio frequency magnetic field at right angles to the main magnetic field. But there also, that is the basic application, if I would say. But you can also transmit it at several other angles depending on what you need and your kind of specialty that you have in the magnetic field. So if you put it together, you are sort of like this. You have the main magnet mostly on the outside. You have the gradient magnetic fields that follow. The shim magnetic fields might come in before the gradient magnetic fields. And then you have the radio magnetic fields. And then you need to amplify some of the signals, of course, and you need to control them and things like that. So these put everything together into what you would call an MR system. I leave some few minutes for questions, if any, but basically this is the end of my talk.